All right, welcome back, everyone. I believe I still have a video to load. I noticed that I didn't have it up. I'll get that up today, along with today's lecture. We are doing 7.5, and this is on inverse circular functions. Or the inverse trig functions. So what do we know about inverse functions? Inverse functions only come from functions that are one-to-one. Now, for a regular function, just a function in general, the biggest requirement for a function is for each input x, there is only one output y. But also, for each output y, there is only one x. Which means our sinusoidal waves, our trig functions are fucked. Think about sine real quick. Sine sufficient to illustrate the idea. One is met easily. One is met easily. No matter where I look for any given value x, there's only one y. I only have one y. But it doesn't go the other way. For every y, let's call that y0, I have repeat offenders, an infinite number of them. Because this, wow, that left fucking sinusoid looks like shit. I've got an infinite number of x values that go. So we're gonna have to address that. We're gonna have to limit. We will need to limit our trig functions. Domains. We'll limit the domains, which will limit the ranges. So 2 is currently not met. When it is met, if a function is one-to-one, it has an inverse. And we usually call it f inverse x like that with an f to the negative 1. It looks like an exponent, but it's not. So let's say we have the f of x, it has a domain and it has a range. So these are x values and these are our y values. When we look at the domain and range of f inverse, they switch. So if fx has a point AB. F inverse has BA. PreCalc is handy. It's probably been a while since you've dealt with inverse functions. F of x and F inverse of x are reflections of each other. Across the y equals x line. Give everyone a chance to comment. I totally did not remember to bring you guys a test. I'll have it on Wednesday. Promise. I go home, as soon as I get home, I'm gonna put them in my bag. And then I'm gonna leave them sitting in the car seat, so I'm looking at them the whole fucking time. That way I won't forget. So far, we're just talking about stuff hopefully you already know. So about inverses, how do we find inverses? So find F inverse. Given F of x. So step one, replace F of x with y. They tend to mean, well, they mean the same thing. And then swap x and y values. Like if we had y equals x squared, it becomes x equals y squared. Just exchange the letters for each other. Step two. Solve that equation for y. Here I would take the square roots of both sides and I get plus or minus the square root of x equals y. And finally, replace y with F inverse. Now, the example I gave here was not 1 to 1. So maybe I would restrict x to be greater than 0. Greater than or equal to 0. That will cover all of the graph. Which means I can't really have a negative square root of x. So y equals x squared looks some shit like this. And I've done a dotted blue line for the part we didn't use. And y equals square root of x looks like this. And that y equals x line is right here. So they're kind of reflected off each other. That's how inverse is working down. Hopefully that rings a bell. Hopefully you've seen that before, it may have been a while. Now we're gonna apply this shit to trig functions. So let's figure out sine inverse. And I'm gonna sketch it real quick. Just a little bit. And it keeps going. So sine x, its domain is infinite. And the range is including -1 up to +1. The sine inverse is gonna have to swap these. But it's not gonna be able to because of the repeats. We do need to capture that range though, the range is gonna be the domain. And it needs to be -1 to 1. So we need to figure out what we're gonna do for the range, and I'll let everyone pause and catch up to what I wrote, because we need to reason out what we're gonna take. Alright, so we need to be able to cover the full range. Let's look at areas that do that. I have -1 here, I could do that up to +1 here. That would capture my -1 to 1. Or I could do 1 to -1 down here, that captures it. There's lots of ways we can capture the -1 to 1. but we gotta pick one. So what they do is they pick the domain closest to 0. So we are going to go with this one. X equals 0 is right there. We're gonna pick that range here. What is that value there and what is that value there? X value.
Oh, X value.
So that negative pi halves and pi halves.
Yeah, negative pi half sounds like a weird way to say it, like pi over 2 is yes. Half of pi in either direction. So that's what our range is gonna be. Negative pi over 2 to pi over 2. We do include those endpoints. And if we think about how that looks. Negative pi over 2. I'll say negative pi over 4, 0. Pi over 4 and pi over 2. We're gonna look at sine inverse this graph. Make a little table real quick. The easiest way to do these is plug them in into the original and figure out what the values are. If I plug in negative pi over 2 into sine, I get -1 is my x. We can see that right here. And we can see pi over 2 is 1. And we see 0 is 0. Plugging in pi over 4 into sine gets me square root of 2 over 2. And plugging negative pi over 4 in gives me negative square root of 2 over 2. So if I were to graph sine inverse, goes from -1 to 1, up to pi over 2 and down to negative pi over 2. Root 2 is like 1.4-ish, dividing it by 2 is like 0.7-ish. So let's see, 0.7-ish, we can't go very far before we're halfway up. Negative pi over 4 has to be around like 0.7-ish. And going the other way, pi over 4 has to be closer to that, the 1 than the halfway mark. So we have something that looks a little bit like x cubed, but restricted. So we can see it's increasing and continuous on -1 to 1. Both the x-intercept and the y-intercept are 0, 0. if I put in negative x. So if like x is negative, if I put in pi over two, not pi over two, square root of 2 over 2. If my x is square root of 2 over 2, I'm evaluating it at negative square root of 2 over 2 is negative pi over 4. And that's kind of like sticking in this value. Sine inverse is an odd function. We haven't done yet. Once we get sine all the way worked out, cosine and tangent will go faster. Seconds, continue. Alright, so coming up with sine inverse. Where does it start at? It's worth seeing. So we have y equals sine x. Well, we had f of x equals sine x. But we restrict the domain and we do that. And now to generate f inverse, we swap x and y. X equals sine y. And it seems kind of weird, like how do we get rid of the sine? The inverse does it. So when we have sine inverse x, it's like doing sine inverse of sine of y. The sine inverse and sine cancel out. But one has to be inside the other. Sine inside sine inverse or sine inverse inside sine cancel. In this one, sine x, x is the angle. So when we swap them, y is an angle here. That's important to remember, because you don't really see it when you're looking at the finalized version. Y equals sine inverse x. This is the angle. And another way to write this, they also call this arc sine. You'll see both notations. Heath was referring to this at the start of class, saw it in the videos. So let's look at some examples. Y equals sine inverse of the square root of 3/2. Or arc sine square root of 3/2. The way to think about this. Well, the approach I use. Is as sine of y equals square root of 3/2. What does y need to be? So if it helps you think about it in degrees. But our final answer needs to be in radians, because we don't plot degrees. So what sign gives us square root of 3/2?
pi/3,
Pi/3.
and one more, right?
So that like theta or y is 60 degrees or pi/3. You also get it with 2 pi/3. Like if you think about going around to the other side, but we're gonna cross that one off. Why? We're doing the inverse, so we have to restrict the domain. And that only goes from negative pi/2 to pi/2. Domain was negative pi/2 to pi/2. Only pi/3 is in that. In this domain. 2 pi/3 is outside of it. And unfortunately. When you take calculus. There's a lot of intervals that require being able to use this. We actually switched to using. Because of the Pythagorean theorem for trigonometry, the sine squared plus cosine squared equals 1. Having that property. Allows us to make substitutions when we're doing calculus, we'll say like x equals 4 cosine theta. And we'll be able to use it to switch to going with something nasty and something nice. And so, but to go into it, we have to be able to come out of it, and that requires an inverse. So, unfortunately, this does come up a lot, so don't just think, this is actually an important section. Keeping that in mind, let's look at another example. What about y equals sine inverse of 1/2?
Pi 4. Or
Pi over
no,
4,
no, no.
yeah. Yeah, it's not pi over 4, it's pi over 6. Sine y equals 1/2, where does it happen? Y equals 30 degrees or pi over 6. It's also at 150 degrees or 5 pi over 6, but that is outside of our range. So we cross that one out. So y equals pi over 6. What about y equals sine inverse of square root of 2? Any ideas? Is there anything that works?
No,
Related to 45 degrees, the square root of 2 over 2, but I don't know how.
Right, it looks like the square root of 2 over 2, but it's not. Square root of 2 is like 1.4. Sine never hits 1.4. If you look at the original sine graph. It only goes up to 1 and square root of 2 is higher than that. So it actually, there's no solution on this one. That's a dirty trick. But it's designed to make you think. Alright, you guys ready to take a look at cosine? No. Cosine, let's take a look at the graph. That one starts high. And goes low and comes back up. Starting to grab my fucking teeth. That left side of the graph looks terrible. So y equals cosine x. Oh, they can go on the fence. I don't know what it's. Well, I need a region that includes -1 to 1. And I kind of want them in order if I can, so that's a possible choice. That's a possible choice. That's a possible choice. So we wanna choose something that's close to zero. Both are close to zero. We do the one to the left or the one to the right. But the one to the left has negative signs, so fuck all that. We're gonna use this choice, let's go with this. That is 0 to pi. So we swap these, x equals cosine y. Or y equals cosine inverse x. Again, y is the angle. The domain is -1 to 1. And the range here is 0 to pi. Make a little table. 0 pi over 4, pi over 2. 3 pi over 4 and pi. Well, y equals 0 on cosine when that is 1. So think about doing, easiest way to get the x's here is do y or x equals cosine of y. So our pi over 4 is √2/2. Pi over 2 is 0. Negative √2/2 and -1. So we have 1 0 and -1 pi. And the halfway marks are like 0.7 on x, so looking like that. So it looks like cosine inverse is decreasing in continuous on -1 to 1. The x-intercept is 1 0. And the y-intercept is 0 pi over 2. And what else did we look at? For sine, we looked at whether it was odd or even. Let's see what we did. Sine. Oh, I'm missing. Yeah, we're increasing continuous on sine, we did the intercepts. Cosine inverse, if I stick in negative x, I am off the graph. Well, I don't have any symmetry. So cosine is not, cosine inverse x is neither odd nor even. Cosine was even, cosine of x was even, cosine inverse is not. Sine was both sine and sine inverse was odd on both. Cosine doesn't have that property. Like if I stick in pi or square root of 2/2. Or negative, and I make it negative. I'm getting 3 pi/4. If it's odd, it would be the same as this, but with a negative sign. And if it's even, it would have the exact same sign. It'd be the same thing, but it's not, it's 3 pi/4. Neither pi/4 or negative pi/4, so it doesn't have that odd or even value. And we'll do some examples. Yep. What is y equals arc of cosine 0? Easier way to think about this is cosine of y equals 0. If you're capable of looking at this without thinking of it like that, knock yourself out. I every time rewrite this in my head as the cosine and I switch it, because it's easier for me to picture. What values of cosine has 0? On the unit circle, it's straight up and down, right? So 90 degrees or 270. Which would be pi/2 or 3 pi/2. But we're only going at pi/2. Because our domain stops at pi, so that one's out. What about y equals cosine inverse? 1/2. What?
Pi/2.
Let's see. Cosine of y is pi/3. Is that true? Wait, that should say 1/2. There we go. So where is cosine 1/2? So sine would be 30 degrees, cosine is 60 degrees, and 60 degrees does match up with pi over 3. It's also 5 pi over 3 here and here, but only this one matches. And we'll do tangent, and then we'll look at some of the graphs of the others. Let's take a 10-minute break. It's been 50 minutes, I don't wanna. Alright, we'll take a look at the tangent function. Tangent does a lot of these. Remember the graph of our tangent? We're gonna go with the one closest to 0, which means we want this range here. So. Our tangent's range becomes tangent inverses domain. The domain here is, the range on tangent is negative infinity to infinity. And that stays, negative infinity to infinity is the domain of tangent. The range is gonna be pi over 2 or negative pi over 2 to pi over 2. But since those are asymptotes, we have to use parentheses, not brackets. And it's helpful to remember that those remain asymptotes. So when we look at the graph of tangent inverse. We have asymptotes going along y now. At pi over 2 and negative pi over 2. I think 0, 0 is easy to see on the graph. And they're gonna, this graph shows asymptotic behavior, which means it approaches the asymptote. The easiest way to remember this without a table. This is positive, positive here, and these are negative, negative here. Which means they go together. The negative side will be in the negative x will be with negative y. So it approaches the asymptote that way in the negative. And the positives go with the positives. So that's gonna do some shit like that. We still have positive, positive when they swap, and negative, negative when they swap. That way you don't have to remember, try to remember the curvature. And tangent inverse is odd. It's an odd function. So tan inverse of negative x equals negative tan inverse of x. Alright, let's look at some examples. Good stretching?
Yeah.
Theta equals arctan of square root of 3. That should say arctan. This is like saying tangent of theta equals square root of 3. And remember that's sine over cosine. So we're gonna need to get our square root of 3 on top, we get square root of 3 over 2 over 1/2. That'll give us our thing, so what angle is theta? Where does sine equal square root of 3 over 2?
Pi thirds,
5 over 3, yeah. Alright, what about theta equals, oh, let's do y equals sine inverse, not sine, tangent. Looking at tangent, tangent inverse of 1. I get -1. We haven't done any negative numbers, 6 fucking negative numbers. So this is like saying tangent of y equals -1.
-1.
What?
Or never mind.
Think about it as sine y over cosine y. For them to have the same, for them to be a positive 1 or -1, these have to be the same value. Right? So that would, the only ones that work with that are square root of 2 over 2. And to have negative. Where is that happening?
2.
Quadrant 2 and 4, and we want quadrant 2. Do I not want quadrant 2?
I wasn't sure, I got to there, then I wasn't sure.
No, it's not quadrant 2, it's quadrant. Yeah, it is quadrant 2. Let's see. Tangents like that. We're looking for -1, it should be over here. That's tangent. So tangent inverse is like that. We're looking for. What y gives us a -1 value? Or what x has a -1 value? We're over there, it should be. Negative pi over 4, because these are both pi over 4s. Just figuring out which one, we got the negative there. Negative pi over 4. Because the domain is negative pi over 2 to pi over 2. So you're right, quadrant 4. You're right. Quadrant 2 is outside of our range. Or quadrant -1. Oh, I like that. Don't do that, don't say quadrant -1, maybe I should not say that. I don't need you going on to calculus teacher and taking it with someone else. Mr. Jones said quadrant -1 and they just fucking go ape shit. Those are the three that are used the most. When we're using them, you can always choose a sine, cosine, or a tangent rather than a secant, cosecant, or cotangent. If you want to see the other ones, we can sketch them real quick. Just some quick examples. So if I looked at secant x. That goes off of cosine. So I'll sketch cosine real quick. And wherever cosine is 0, we have an asymptote. And it does some shit like this. That's secant. So secant's range is -infinity to -1 in union with 1 to infinity. We need that to be the domain of secant inverse. And the way they do that, we need to have the positive branch and we need to have a negative branch. They choose this one and that one. And we have an asymptote in between it. The range it will be. Because the domain of this secant to get that is 0 to pi over 2 in union with pi over 2 to pi. So that'll be the range. And this graph looks super weird. We have an asymptote at pi over 2. And does some shit like this. Fucking weird. Just so you've seen it. Oh, fuck. Share screen, do that. Go quickly, there we go. So that's secant inverse. I'll show you cosecant inverse and cotangent, then we'll write down their things real quick. Cosecant inverse does the same thing, but an opposite way, and the asymptote is at 0. And cotangent's kind of like tangent inverse. It's gonna be doing some shit like that, but it's shifted. It goes up. Cause it's based off of the domain of cotangent. So let me change back over and we'll write down what they are and then we'll just. I'm not gonna do any examples with secant, cosecant, and cotangent, but I wanted you to see them. We'll sketch those real quick. I showed them on the screen. Cosecant inverse. It does some shit like this. The asymptote is along the 0. And it goes like this. So domain is negative infinity to -1. In union with 1 to infinity. And our range is -pi/2 to 0. -pi/2 is included, the 0 is not. Up to pi/2. And also for your notes, cotangent. That is at pi/2. It crosses there, goes up to pi. Pi and 0 are asymptotes. It's like tangent had asymptotes, cotangent has asymptotes. And this one is positive over here. So the domain is negative infinity to a positive infinity. And the range is 0 to pi. Just so you've seen them. Alright, you guys ready for some examples for like how we'll use all this shit? Other than just finding values, which is the boring part, a calculator can do everything we've done so far. Alright. Couple people stood up. So find, evaluate without a calculator. Cosine of sine inverse of 2/3. So a way to think about this is like this is cosine theta. Which means theta equals sine inverse of 2/3. Which means sine theta equals 2/3. Sine goes from -pi/2 to pi/2. Sine's positive in quadrant 1, so we will make a triangle in quadrant 1. Using opposite over hypotenuse. 2, 3 there. Call that A. So A squared plus 2 squared equals 3 squared. A squared equals 9 minus 4. Where A equals square root of 5. That should say is 2 squared right there. Like I took the square root of both sides. Alright, we wanted cosine theta. Cosine theta should be adjacent over hypotenuse. Square root of 5 over 3. Are there any questions? I need to go over anything again.
Could you explain why we got a positive square root of 5, like how are we with in quadrant 1?
Cause sine theta, we remember, we're looking at sine inverse. We need to include all of sine's positive and negative values. Which happens in quadrant 1 and quadrant 4. So we're going from -pi/2 to pi/2. And if sine theta is 2/3. This is in quadrant 1. So like if I put my axis here. I deliberately put my triangle in quadrant 1. Does that make sense? A is x. X is always gonna be positive on this side. That's how I got positive square root of 5. Does that make sense? Doesn't look like it's clicking. Where is sine theta positive?
I think positive is 1 and 4, quadrant 1 and 4.
No, sine theta is positive in 1 and 2. This is y. Remember, like y is our sine and x is our cosine. So sine is positive in 1 and 2. But our domain of sine inverse is these two.
Okay.
So like sine's positive there, but our sine inverse is here, it's gotta be in quadrant 1. I don't know what angle theta is. It's gonna be some calculator. If you needed the actual angle, you would need a calculator because 2/3 is not on our table. But we don't need the actual angle, we just need cosine of the angle. So if you build the triangles, those in the right quadrant, just remember how x and y should be in that quadrant. So if theta had been sine inverse, if we had had cosine of sine inverse of -2/3. Then we would have been in that quadrant. And the -2's here, because that's a y value, the 3 is the hypotenuse. We're still gonna end up with a square root of 5. And cosine of theta would be the same. It would still be square root of 5/3. Because it's adjacent over hypotenuse. That's kind of cool. That's fun. Let's do cosecant tangent inverse of 3/4. So this is like doing cosecant theta. If theta equals tangent inverse of 3/4. Which means tangent theta equals 3/4. And that's opposite over adjacent. So if you're picking where it goes. What quadrants is tangent positive in? Tangent's positive in 1 and 3. But 3 wasn't in any of our domains for the inverse. So that's gonna mean our triangle is locked into quadrant 1. That's outside tangent. Does that make sense? Does that line up with what we said about tangent? Tangent inverse's domain was -pi/2 to pi/2. And if that's our theta right there, we are in that range. What's wrong, Jordan?
For my notes, I had domain is -infinity to infinity. But I must.
Yeah, sorry, that's the range, sorry.
Okay.
And that's the domain of tangent. And that's what we're looking at, we're looking at tangent right now. You're right. I said that right, wrong. So it's the range of tangent inverse, but it's the domain of tangent. And that's what we're looking at, we're looking at tangent theta equals 3/4. We know it's gonna be quadrant 1 or quadrant 3, because that's where tangent's positive. But it's gotta match. The right quadrant with the inverse part of it. And tangent inverse is in these two. Again. Tangent inverse is here. So we're there. We put our 3 here, that's opposite over adjacent would be 4. What is the hypotenuse?
5.
5. This is a really well-known triangle. 3, 4, 5 triangle. But you can see that if you didn't know, 3 squared plus 4 squared equals c squared. 9 plus 16 equals c squared. So C equals the square root of 25 or 5. So that, what did we want? We wanted cosecant. So cosecant is 1 over sine. Sine is normally opposite over hypotenuse, which means cosecant is hypotenuse over opposite. Which on this one should be cosecant of tangent inverse of 3/4. Hypotenuse is 5, opposite is 3, 5 over 3. Is that not super fun? Don't worry, you'll have more fun like this on your homework. I don't think we've had enough fun yet, though. Ooh, dun dun dun, this is some serious dun dun dun. Everyone ready? Sine. I heard the button hit, okay, sine of arctan. Of 4/3. Minus arctan. Nope, let's do arc cosine. Arc cosine of 12/13. So this kind of looks like sine of A minus B. If A is arctangent of 4/3. And B is arc cosine of 12/13. What's this formula for sine of A minus B? Anyone got that memorized yet?
Sine A cosine B minus sine B cosine A.
That'll do, donkey, that'll do. That's some Shrek for you, I'm not calling you a donkey. That's exactly right. So we're gonna need those. So maybe let's do some triangles. This is saying tangent of A is 4/3. Which would be opposite over adjacent. And this is saying cosine of B is 12/13. And that's adjacent over hypotenuse. So I'm gonna make 2 triangles. It looks like what quadrant should A be in? Where's tangent positive?
1 and 3, so we'll grab 1.
We're gonna make quadrant 1 here. What about cosine B?
1 and 4.
No. Sorry. Cosine is positive in 1, 4, yes. Which quadrant are we have to pick though? What overlaps with cosine inverse? So you said quadrant A will be that one, that'll be A. We said cosine is positive here and here. But for cosine inverse, we need to include the full range of negative and positive values. So maybe I'll do this in different color, cosine inverse. Has to include negative and positive values. It's here and here. That has our negative and positive of cosine. Cosine inverse is 0 to pi. This is actually a helpful way to think about it. Like I need the full input range of cosine. For the inverse to have a negative and a positive. So where's cosine positive and negative? Those are the two that are closest to 0. For sine or for tangent over here. Tangent's positive here and here. But tangent inverse has sine over cosine. Tangent inverse is positive here and negative here. We need those values. So that quadrant there and this quadrant there as well. It takes some wrapping your brain around until you line up what quadrants what. So A is over here. And we said B is over here, so put my B triangle in. Opposite over adjacent, 4 over 3. We just had this, we had a 3, 4, 5 triangle, that's that. B is adjacent, which is 12, and the hypotenuse is 13. Well squared plus B squared equals 13 squared. That's 144 and 169. B squared equals 169 minus 144. B is the square root of 25.
B is 5.
So B is 5. 5, 12, 13 is a known triangle as well. But if you're not in architecture, you probably don't know them very well. So now we need sine A cosine B. So sine of A minus B is what? I'm gonna rewrite it again here and I'll just write what we're looking for below it. Sine of A is opposite over hypotenuse, 4/5. Cosine we already had, it was 12/13 for cosine B. And we got minus sine of B. Sine of B is 5 over 13. And cosine A is 3 over 5. $48 minus 15 over 5 times 13 is 65. That 33 over 65. Does that make sense? A lot of work on that problem, right? We're not gonna walk through a full example, but if you see something like, because there's another full example I want to do, and we got 10 minutes left. If you see something like sine of 2 times any function inverse. Let's say negative 5/13. Don't try to make this whole thing theta, just make that theta. This would be sine of 2 theta. Which is 2 sine theta cosine theta, and you only got one triangle. But you gotta do the triangle thing again here. Go off of that. In fact, if you do work this one out, you are in quadrant 2. And if you work it out, you will get -120 over 169. So if you want to try your hand out later. And having known answer, you've got one there. I do want to give another one where it's a little different. Because here we've given values, but let's do one where we don't have values, we have a variable inside. Because this next example shows up a lot in calculus. Well, variance of it, I should say. We'll do a lot of stuff like cosine of tangent inverse of u. Where we don't know what the value is, u is our variable here. I don't want to say x because we're going to plot it on an xy graph. So I'm just going to say u. So this is my theta. So tangent theta is u. And tangent is opposite over adjacent, right? So what do I gotta use here? Do I have a fraction? Yeah, I just have u, and I make a fraction. How can I make turn a whole number into a fraction without changing its value? It's over 1, yeah. We'll use over 1. Kind of have like 2 options here, don't I? But whatever I come up with, it shouldn't make a difference because I'm looking for cosine. Cosine is going to be positive no matter which way I do it. U over 1 would be that. I guess this is like, no, that doesn't work. That's a negative value. That one's out. I've only got one option. So what does that make the hypotenuse? U squared plus 1 squared equals c squared. So c is the square root of u squared plus 1. And so we want cosine of that angle. Cosine of theta is adjacent over hypotenuse. 1 over square root of u squared plus 1. And if we wanted to rationalize it, we multiply the top and bottom by u squared plus 1. In calc, this is the form you will see more of them. You'll be working with stuff called integrals, and you'll have some shit like x squared plus 1 and the square root on bottom. And you gotta recognize we could treat that as either as a cosine or a sine. You'll see when you get to calculus where it happens, but this does show up. And I got a few minutes left, let's do one more. We set it up. Cosine of 2 sine inverse u. So this is like cosine of 2 theta. If theta equals sine inverse u. Which means sine theta is u. Or u over 1. Now we can do the triangle thing, and we will. Sine theta will have positive. Because sine inverse is quadrant 1. Opposite over hypotenuse. And when you calculate this, you're gonna get 1 minus u squared down here. We have 3 options for cosine tangent theta. What are my 3 options for cosine, or not tangent theta, it's cosine of 2 theta? We can do cosine squared theta minus sine squared theta. We could do 2 cosine squared theta minus 1. And we could do 1 minus 2 sine squared theta. Those are my 3 options for cosine of 2 theta. One of these is substantially easier than the other 2. Well, prettier looking when you're done. But they should all clean up to the same thing. Which one looks like the prettier one to enter?
1 minus 2 sine squared theta.
1 minus 2 sine squared theta, because we're doing like opposite, this is opposite, adjacent, hypotenuse. If we have cosine, we're gonna have the square root thing, we gotta deal with it. Sine theta is the better one. So cosine of 2 theta will be 1 minus 2 sine squared theta, which is u over 1 squared. So 1 minus 2u squared. I didn't actually need the triangle for this. I already had sine theta. So if you look ahead and rationalize, think about some shit. And you knew which formulas we had an option for, and you already have everything for one of the answers, just use it. All of these will get you there though. This one would be 1 minus u squared minus u squared. And that one is 2 times 1 minus u squared minus 1. But you clean both of those up. And you get that. Alright, have a good day, get the fuck out, peace.